Thank you. Thank you very much also for giving an introduction to my talk. So it's a pleasure for me to be here finally. Ask me privately what happened. It's really a nice story, right? That goes back 41 years and caused me troubles. Now, the content of my talk is I would like to talk a little bit on MFM, how to obtain the highest sensitivity using cantilevers that have an incredibly high Q without Q control. And I think that's important. And I again want to reiterate what Romain already told you shortly, how, what happens if you do a normal frequency scan, and I have some images, what really happens if you scan too fast. So that may be interesting for the students. And then I show you, like with that sensitivity, what you can do. But if you have an increased sensitivity, you can do a lot of nice things, but you also discover, oh, there are some backgrounds in our measurements that we need to understand. So we can get improved resolution and, of course, do tip calibrations. Then what is super important is we want to be reliable and reproducible in our imaging. So what that means is even a week later, you start a measurement day one, Monday, and then maybe a week later, you want to do exactly the same measurement, because only then, if you're able to do that, you can compare different samples, or you can compare measurements on one sample in different magnetic fields. So that's super important. How do we do that? And how can we disentangle the forces? And then moving on to more the atomic resolution work, can we do AFM, KPFM, and MFM together? So using all these multi-frequency, multimodal techniques, and I will show you one small example. So some words about our control system. We use a very simple home-built control system consisting of an NI real-time system is 16 bits, DUX, 16 bits ADC, and the analog digital converters we actually also use to read, the four outputs, analog outputs given by the Zurich Instruments. Now, we do that because we want these signals to be in real time, because we have some feedbacks implemented in our controller. But what we also do is, there's a backside on the Zurich Instruments, and it provides you with some digital signals, and we also read these. But these, they are like coming at the time base of the Zurich Instruments lock-in, and that's not our scanning time base. So we send these signals and we record them with a timestamp, and our PC later fills it into the image. So if you're a user, you see the points coming point by point, but it's not actually a real-time signal. We call it a pseudo-real-time signal. Now, why are we doing that? We are doing that because 16 bits are not enough. And of course, it's almost impossible to get more than 16 bits. And to give you an example, if you have, we have a frequency span from 25 hertz to minus 125, which we transmit to plus minus 10 volts with 16 bits, we get 2.3 millihertz per bit. And that's not enough, right? We can measure sub-millihertz signals. So that's not enough, and that's why we need a digital signal transmission. Now, talking about the noise, there is this very well-known equation of the thermal noise, and what we need is basically, we need here, now the laser pointer, does it work? Yeah. We need a low stiffness and a high resonance frequency. Now, you may think that it doesn't matter, right? If you go to a stiffer cantilever, both goes up, the stiffness and the resonance frequency. That's true, but they don't go up in the same way. Actually, the stiffness increases much more than the resonance frequency. And if you look at the equations, you basically find that it is good to use a long and thin cantilever. Looking also at the quality factor, you have these various losses, like the molecular losses, the friction of the cantilever in air. So let's go to vacuum, as we all do. But then there are other losses, like the support loss here, and also the surface loss. And actually we discovered for these long and thin cantilevers, the surface loss that arises from the coating we put on the cantilever. And remember, we may want to have a mirror coating on the backside, and if you want to do electric measurements or magnetic measurements, you have a conductive coating on the front side. And that coating actually induces a lot of dissipation. It's the grain boundaries between the polycrystalline coatings where you have a lot of unhappy atoms. So these are atoms that are not in a crystal lattice that you can nicely strain and destrain, but they are, between lattice cells, and they hop like in an amorphous material, and that's causing dissipation. So what we do is we limit the coating to the very end of the cantilever. We coat the cantilevers by our own spotter deposition system, and we have a mask implemented. And like this, we can get cantilevers that have a quality factor. Sometimes we reached up to 1 million. Now more standard is something between 200 and 400,000. And if you compare that, that table gives you the comparison. For example, for a cantilever used for an MFM in air, you end up with about 4 millinewton per meter per square root of hertz of noise. And if you go to vacuum, see we can gain up to a factor of 100. And now to lose a word about tuning forks, which are very fashionable for atomic resolution in vacuum, they're not good for MFM. I don't know whether Franz is here, he probably contradict. But if you just look at the noise figures, you know, the noise figure actually, even at low temperature, these are all room temperature noise figures, that's very bad, right? So you have to use these soft cantilevers. Now, talking about these high Q cantilevers, here's the problem that Romain already mentioned. If you scan the resonance frequency at a reasonable rate, right, you get all this beating. And that's simply because you don't reach the steady state of the differential equation. And that's, of course, a problem. So what's the quality factor? And actually, Romain already said how to handle the problem, right? So you have to scan slower, but if you scan slower, be aware that your resonance frequency may also drift. And that's also the problem if you want to close the PLL, that your resonance frequency may have drifted away. It's so sharp. I mean, look at the figure here. This one it's the same cantilever in air, and that's the same cantilever in vacuum. So it's 0.3 hertz wide on this roughly 70 kilohertz here. So that's a sharp resonance. It's even a problem to find it initially. So how we find it is usually by a thermal noise analysis. And then we do a local sweep. We don't care about the beating. We may do a slow sweep knowing that this is not correct, close the PLL somewhere, and then do this phase sweeping as introduced by you. So that works very well. And now we have this high Q cantilever. That's the comparison. On the left side, you see an image done in air, and on the right side in vacuum. And obviously, you see the noise is gone. It's much better. And you can do now, because the signal to noise is so nice. And remember that we read these signals also digitally. So we have more than 16 bits. We can do sub-millihertz readings. And what you can then do is you can look at these asymmetric domain walls that you see here. If you pay attention to this is more white at the bottom and more dark at the top. So it's asymmetric. It shouldn't be like this. It should be symmetric. And that asymmetry actually comes from the canting of the cantilever towards the surface. We're actually not measuring the normal force, but the canted force. And we also do the derivative along this canted direction. And this leads to a phase shift between high and low spatial frequencies to a distortion of these domain walls. And since we understand the imaging process, we can correct that. And that's the deconvolved image with perfectly symmetrical walls. And we can also correct for the distance loss. You have to measure a little bit away from the surface. And that, of course, the signal is lost. If you go further away from the surface, the stray field decays. And we can calculate it back to the surface to get a much sharper, higher resolution image. So that's all possible, thanks to the super high quality factors that we employ, and thanks to the Zurich Instruments permitting us to read the signal digitally for further processing. Now that's an image, right? And what you show here, this is a 3-atom thick magnetic film. And we record a stray field of a 3-atom thick film. Actually, we can also measure monolayers as long as they have domains and generate a stray field. And you may say, yeah, but there is a lot of noise in these figures. Well, that's actually real noise. That's noise given by the sample, not by the measurement. That's because nobody in the world can fabricate a magnetic film that's perfectly 3 unit cells thick. The thickness actually varies. And also the anisotropy axis of the grains of this polycrystalline film, they vary, and that gives that generates a stray field or a noise in a stray field, and we can pick it up. First you're surprised, you're improving your measurement, and then you end up, oh, I see a new kind of background here. And then you need to understand it. So that's what we have done here. Now, if you do like Kelvin probe and MFM in air, you usually use this tapping, and then you retract and you do lift mode. Now in vacuum, you can't really do that because the energy loss per oscillation cycle of my cantilever is very low. So if I start to tap on the surface, I lose maybe an electron volt per tap. So that's much more than I use when I operate my PLN normally. So the PLN just doesn't work anymore, it crashes. So we cannot do tapping. So how can we do reliable distance control, right? Now you would probably do a frequency shift feedback, right? Keep the frequency constant. That's what we do if you record atoms. That doesn't work here because the frequency shift can be repulsive or attractive. We have magnetic forces, right? And we also don't want to measure at different local heights. We actually want to fly over the surface at constant average height. And to do that, we actually use a technique like FM Kelvin. So we excite the tip sample potential at some, let's say, at the kilohertz frequency. And of course, the tip sample that forms a capacitor, and the energy of that capacity is 1/2 Cu squared. And of course, if you take the derivative of this energy, you get the force, and to get the frequency, you take the second derivative. So we take the second derivative of the capacity here. And here you have U squared with the first sideband that is usually used for Kelvin. So in Kelvin probe, you null that sideband. But we are actually using the second sideband. And as you see, the amplitude of the second sideband does not depend on the local contact potential difference. It only depends on the UAC that you apply and on the tip sample capacitance, which is a measure of the distance. So looking at the amplitude of the second sideband tells you actually where you are above the surface, or at what distance you are. And we use that for a slow feedback. That's a bit challenging because these signals are so small, right? They're a few picometers, typically, for a 5 nanometer oscillation amplitude. Now, how do we do it? Maybe this is too much detail, but we use, the first lock-in here for the PLL and the second lock-in on the second sideband, so recording the second harmonics here. So in the modulation tabs, we go to the second harmonic. And then this is a little bit complicated, and I never understood why it needs to be like this. Maybe we can discuss that later, right? We use actually a PID to measure that amplitude signal. And we don't use it really as a PID. We just have a P value here. We don't have an I value. And that's just to output the signal amplitude of the sideband, to some AUX3 here that we use. So that's a little bit a strange implementation. But, there is always the schematics, the equations, and then you have to figure out how do you actually implement it into this or that box. So that's shown here. Now, what do we use it for? This is one of our multi-layers that we measure. And you see, we repeat here, iron, cobalt, and you don't have to remember the details here, but this is a system that generates these small magnetic bubbles called skyrmions. And here we have some rare earth multi-layers. So this is a very complicated system. And please believe me, we know what each of these layers does, and we can also measure the macroscopic properties. And what you get is you get two different skyrmions. And that's what we're interested in, having a bit 1 and a bit 0 in the same sample. So two different types of skyrmions coexisting in one material. And then you need to figure out in which layer do these skyrmions actually exist. And for that, we use differential imaging techniques. So we play Lego, we disassemble our sample. So that means we don't disassemble it. We grow different samples consisting of parts of these many multi-layers that I've shown you before. And then actually you must be able now to measure these 6 samples on the absolutely identical conditions. So no tip changes are allowed, right? And you have to have the same distance, even a few days later. And thanks to this sideband, second sideband control, that's possible. So we can measure on all these different samples, in exactly the same way. And that permits a quantitative evaluation of the contrast. So we can fit all these skyrmions, we can quantitatively compare those and figure out, these weaker white skyrmions that we have. Somehow the pointer doesn't really work. So these white ones here and the dark ones, in which of the layers do they exist, right? We figure it out like this. But then, of course, nobody would believe us. So we also do micromagnetic modeling, or some colleagues do that. So they can model this and they can figure out where these objects exist. And once again, You know, experimentally, this is only possible because the distance feedback becomes so reliable. Thanks. Now here I show you, the separation of topographic and magnetic signals. So if you scan at, constant average height, you of course have a variation of the local van der Waals force, and it also shows you up in the image. So the so-called magnetic image that we record looks like this. And what is topography and what is magnetism here? Now, to go back, right, why do we do these cylinders? This is actually for a biomed application. This is called a synthetic antiferromagnet, and it gives us a very nice hysteretic loss that we can use for hyperthermia, so to treat tumors. And we invented these particles, and it works very well with those. And we analyzed them by MFM, and obviously, what you have to do here, again, having reliable tip sample distance control, we can flip the magnetization of the tip, and you can have images taken under exactly identical conditions with opposite magnetization of the tips. And then adding and subtracting the two sets of data gives you, on the left side here, the van der Waals image of the surface. So basically you see that you scan above a cylinder that sticks out, above a table mountain that sticks out, which gives you a negative van der Waals contrast. And then if you subtract this from the initial data set on the top, you get the bottom two images. That's the purified magnetic signal. So that's again possible because distance control is reliable. Now, can we also measure non-flat samples? Yes, of course. It gets more challenging because this tapping lift mode doesn't work. So we have to have, again, a non-contact mode. And we use this sideband now to have a local feedback. So we really locally follow the topography. The only problem here is, again, noise. So what we need to do is we need to have a larger oscillation amplitude and a larger electrostatic oscillation amplitude, and only then distance control locally becomes possible, but it's very slow. So you have to scan with 3 seconds per scan line. So forward and backward is 6 seconds over some microns, although, right? So it is slow, but it works well, and this is a sample fabricated from PSI. They wanted to understand the influence of the curvature on the local magnetism. But let me skip that. That's about tip calibration, but let me show you the results. So this is again, we measured magnetic signals, and usually now people go and say, what's the diameter of these objects? And I always say, no, please do not look at the image and determine the diameter of your object from that. That's how your magnetic object appears after you image it. But you image it a certain distance away from the surface with a tip that convolutes the stray field, right? So it's not the correct diameter. But again, thanks to the excellent signal quality, we can calibrate the tip and we can deconvolve these images, and we actually can get the magnetization pattern. And now that's the right diameter. Now we can go in and look at these bumps, and fit some Gaussians to it and analyze the diameter. So that works very well, but only thanks to the good signal quality, because deconvolution is always bad. It's always terrible, right? It's easy if you start and then you apply these transfer functions to go to the frequency shift, but it's more challenging to go backwards, because in that process, going from the magnetization to the stray field to the frequency shift involving the tip, you add always a little bit of noise, you lose a little bit of signal, your signal to noise matters. So going backwards is more challenging and only possible if your SNR is super high. Now that again shows you, like if you change the material properties, we can get much smaller skyrmions, and here, 26 nanometers in diameter. So people ask me, what's the resolution? Well, I don't know. If you take the radius, it's 10 nanometers, but it's probably better. It's the object size that we image here. So the resolution of MFM can be excellent if you perform these techniques. Now let me show you these multimodal measurements. So what I show you here is nickel bromide deposited on a gold single crystalline surface. And here we first did simultaneous STM and bimodal AFM. Now, nickel bromide mono and bilayers are predicted to be ferromagnetic with an in-plane magnetization. And we thermally evaporate this nickel bromide, and it's known that, out of the Knudsen cell, you get dimers and monomers. But if you have these monomers coming down to the surface, some of them split up. So you have a dehalogenation, and you can see more of that for manganese iridium, manganese iodine on Daniel Rothard's poster, and also in my talk on Friday morning. Now we do atomic resolution, STM and AFM, using a fundamental mode, a hard cantilever with about 40 Newton per meter cantilever. So the second mode is about 1500 Newton per meter with two different amplitudes, as again indicated by Romain. That's exactly what we are doing. We are doing tunneling through the tip, and we run, a constant STM feedback here at 10 picoamp, and we map the time averaged delta F2 signals. Now you may ask, why do we need the delta F1? Well, we actually needed to do Kelvin. I will show you later. Now that's the results. So you see here on this image, you see that the nickel bromide actually decomposes on the surface, and it forms this spider web here. And if you zoom in, this spider web actually consists of single bromine atoms. So some of the monomers coming down, they split up, and you get this spider web of bromine atoms. Now, you get less bromide. So what happens to the nickel bromide? Well, the nickel bromide actually forms now two phases, a so-called nickel bromide X phase. So that's a bromide deficient phase that shows this kind of superstructure here. And on top of the superstructure, that's at least what we find, or embedded into this superstructure, you find the nickel bromide islands. Now, how do we know that these are nickel bromide islands? Well, we can simply zoom in. And if you zoom in, then you get the atomic resolution of this nickel bromide lattice, and it just, it matches the expectations of DFT. So density functional theory gives you how it should look like and what distance you should have between the atoms. And here it's 3.7 angstroms, and it matches that very well. So now, of course, what is Kelvin helping us here? Now, to study the magnetism, we want to go a little bit on a larger scale, right? We want to move away from the atoms and go to a scale like this, where we don't get atomic resolution, or even larger scales. So that's why, you can do Kelvin here to identify the Kelvin contrast you get on these specific structures that you see here. And then once you know that, you can look at the larger scales where you don't get atomic resolution, but you can still do Kelvin, and you can say, okay, if I get this Kelvin contrast, it must be this island, and then also look at the magnetic signal. And that is what is done here with bimodal and multi-frequency AFM. Now, this has already been introduced. It's trivial to use two PLLs to lock on the first and on the second mode of the cantilever. Now here, we use a very soft cantilever, 0.5 newtons per meter. Now why? You learned that in my first part, in the first part of my talk, right? We use these super soft cantilevers because it provides us with this excellent sensitivity. After all, we want to measure the magnetism of a single monolayer. And also we want to have a decent bandwidth for the Kelvin signal. So we use the first mode to measure the magnetic signal, and the side bands of the first mode to measure the Kelvin signal. So having this high sensitivity, and then to get, the atomic resolution, or let's say the nearly atomic resolution, the atomic step resolution on a larger scale, we use that additional second mode that is now a cantilever with about 20 newtons per meter, right? If you multiply the 0.5 with 40, and we use the second mode in a constant delta F feedback to get the structural resolution of the surface. Now that's shown here. And of course, now here comes the game with the two different amplitudes, has been worked out by Shigeki Kawai earlier on in Basel, right? If you use this large amplitude, you average over your oscillation path of the tip. So your first mode is sensitive for the long-range forces, so the magnetic and electrostatic forces, where your small amplitude second mode is a time average signal that is sensitive to the short range atomic or van der Waals forces. That's what we make use of here. So multimodal, right? First and second mode, and multi-frequency using the sideband techniques simultaneously. Now, how do we do it? Well, in the same way as before, right? We have the PL working here on 58 kilohertz. That's the first mode. We have the second oscillator here working at 350 kilohertz roughly. That's the second mode. And then we have the electrostatic actuation. So that's 1.1 kilohertz. And you see these two modes. So the first mechanical oscillation mode and the second one, they're outputted, on the first output, going to the mechanical excitation of our cantilever. Whereas the 1.1 kilohertz signal is outputted here on the second channel, and that's going to the tip sample potential. So all this is possible thanks to this instrument, the Zurich Instruments, and we can now record, use the modulation tab with the two sidebands. And I remember for the distance feedback in MFM, we used the second sideband. Here for the Kelvin, we use the first sideband, and actually we use, a PID2 here for the Kelvin feedback with a proportional and integral factor that we figured out to optimize the speed of the Kelvin signal. And we use the PID4 again in this very strange way to also output the error to one of the AUX outputs that we can read. So that's how we operate the instrument. And does it work? Yes, it does work. This is the topography. And I have to apologize a little bit. This is not the nice looking gold surface, but that preparation was done by my former PhD student who was a little bit less talented. And thanks God, I have now Daniel Rothart, who also gives a presentation, a poster presentation, and he's really talented. He knows how to prepare this surface in a better way. But these are initial experiments. And what you see here are the steps of the gold surface. And you see all kind of junk on that gold surface, right? And that's the the bromine network. And you see the nickel bromide X phase, and you see the nickel bromide. But what is what? From the topography, that's very difficult to tell. And don't make the mistake to look at cross sections, right? Because, this is AFM, and, if you have different materials, you don't really get the correct heights as you get in DFT. So it's very difficult to see what is what. But of course, we can zoom in and get atomic resolution. And then we can do Kelvin simultaneously. And then we can use the Kelvin to identify the phases. And that's what we have done here. So in blue, that's actually, a CPD difference of 1200 millivolts. What you see there is the bare gold surface with the bromine mesh. Well, not atomically resolved. This is a large scale, as you see. And then you see the nickel bromide X phase. That's the green islands. And on top of some of these X phase islands, you see the nickel bromide, the actual phase we want to study. So that's Kelvin measured simultaneously on the sideband of the first soft mode with the topography. And now again, simultaneously, here to measure the topography, we keep the second mode frequency of the cantilever constant, and that's actually the travel of the Z piezo to get, a constant delta F2. Now, we simultaneously record the delta F1. That's the frequency shift of the first mode. And now, it's not shifted by the electrostatic signals, because the electrostatic signals, the local ones, we compensate them with our Kelvin control. So what is left over is the magnetic signal. And that's what you see here. Now, you see basically the island structure with a little bit of noise. But what the hell do these red and blue bars mean that you see there? Well, that means positive and negative frequency shift contrast. And that's caused, by the magnetic fields that are generated these islands. Now, these arrows, they indicate the direction of the magnetization inside these islands. So you have a magnetization like this, and the island is finished here. So when the magnetization vanishes, you get a magnetic charge at the edge of the island. And now if you're scared about magnetic charges, if you learn in school there are no magnetic charges, that's not correct. Divergence B equals 0 doesn't mean there are no magnetic charges. There are no magnetic free charges, but they're bound charges to the surface, and you can introduce them in the same way as you introduce electrostatic charges in Maxwell's equations. So if the arrow points like this, you get a positive charge, and the other end you get a negative charge. So you get a stray field emanating from the surface and getting back into the source at the other side. And that's exactly what is seen here, with a resolution of, less than 10 nanometers. Now, are we really sure that this is the magnetic signal? Well, we did a lot of tests because we weren't sure ourselves, right? And it's still not ready for the publication. But what we did is the following. We measured with a non-magnetic tip, but unfortunately in another part of the surface, we didn't find these signals. Unfortunately, in this instrument, we cannot flip the orientation of the magnetism, but we will try to do that later. Now, what we have done here is this is imaged while we follow the topography. So would we get a similar signal if we measure in constant average height? Yes. Could this be signals generated by the canted oscillation of the cantilever? We check this by reducing the oscillation amplitude to a very small level and measuring far away, and we still have these signals. Is it a Kelvin feedback error? We measured with the Kelvin feedback switched off, and we applied different potentials, like 2 positive, 2 negative, just in the middle of the two systems, and it always comes back. So these red and blue lines, they seem to be robust. Now, what about the direction? We also wondered, why the hell do we have this direction? Well, the sample was cooled in a field. Now, in what field? Earth's magnetic field is always there. And we checked in our lab, what's the direction of the Earth's magnetic field, the in-plane there, and it's exactly this direction. So, okay, right? I'm always very skeptical as a scientist. We have to do this again. For the moment, just take it as an example. What can be done with an AFM using such a fantastic instrument? And I'm not paid by them, right? I really like it, right? It's sometimes a bit complicated to use, right? Because how you implement it from that block diagram you have, in your mind as a physicist or electrical engineer, and how you really implement it in the Zurich Instruments lock-in, that's a bit challenging. But once you figure it out, it works very well, very robust. It doesn't drift, right? We have this high stability quartz option that we really need here, because if you have drift, it's drift in our instrument. It's the temperature that affects the cantilever, but not a low temperature. Everything is stable. So these things work very, very well. And of course, the physics still needs to be explored further. And that brings me to my conclusion. I think I have shown you that the ZI permits, this multi-frequency, multimodal AFM operation. I'm sure we see much more at this conference, but I already said it remains a bit challenging to set it up sometimes. Now, the capacity frequency modulated distance control, that works very well with high Q cantilevers for advanced MFM. And here again, the frequency stability of the ZI is crucial. And we can image at constant average tip sample distance, which is the preferred mode mostly, giving topographical perturbations, and you can do differential imaging to get rid of them. We can also do local constant height scanning with somewhat more challenges concerning the low signals. But it is very reliable and reproducible, permitting a lot of different measurements on the same samples or on one sample in different magnetic fields. And that's what you need to do if you want to do magnetism. Now, the multi-frequency and multimodal imaging for simultaneous mapping of the topography, local CPD and magnetic signal using soft cantilevers, to get the sensitivity, but at the same time to get the atoms. I think that's probably the future of simple AFM. And what do I say? Simple AFM, pure AFM, not AFM with, high frequency electric or magnetic excitation or STM done in this way, which is also very fascinating. But, with our limited personal human resources in our lab, we won't be able to do it. So we have to stick to this rather simple AFM. With that, I've come to the end of my presentation. Thank you very much for your attention and taking your questions now.
you.